Okay, in this video I'm going to discuss an example from the text in which there is a certain medical treatment, and each time that medical treatment is given there's a 0.2% probability of an immediate severe side effect. So this medical treatment would probably be for something, for a condition itself pretty severe, otherwise you wouldn't want to deal with that high of a probability of an immediate severe side effect. And what we're going to be concerned with is the number of times the treatment is given if we stop after the first such side effect. And I give a little bit of a description of how this distribution comes about in the text, but I think a video lecture on it would be very helpful. So x can have what kind of values? Well, I want to use set notation here. My random variable x is the number of times the treatment is given. So that could be 1, it could be 2, it could be 3. It's got to be some positive integer. Now it turns out there's no upper bound, so it's just some positive integer. That's the possible values for x. So when I draw my chart for the distribution, do that here. This is a discrete distribution, so I'm going to draw a chart that lists the probabilities. We'll find that that isn't the way we analyze continuous distributions. Then my first possible value is 1. Okay, now what's the probability that x is 1? That's the probability that the treatment is given one time and I stop after the first such side effect. Well, that means that I had the side effect on the first try. And the probability of that happening is 0.2%, in other words 0.002. Okay, now the next possible value is 2. Now how does that happen? That means the treatment's given 2 times where we stop after the first such side effect. So the second treatment must have resulted in the side effect. That's why we stop. Whereas the first treatment did not result in the side effect, or else we would have already stopped before the second treatment was administered. So the probability that the first treatment does not result in the side effect is 0.998. It's 1 minus the 0.2%. And then the probability that the second treatment does result in the side effect is 0.002. And I'm going to look at one more so that we'll see the pattern. And I'll just let my chart stop there. We'll put dots to show that it continues on. Okay. What's the probability that I give 3 treatments and then I stop? Well, that means the first 2 treatments did not result in the side effect, and that happens with probability 0.998 squared. Probability the first treatment doesn't result in the side effect is 0.998, and the probability the second treatment doesn't result in the side effect is the same. And then the third treatment does result in the side effect, which happens with probability, sorry for cramming that in here, of 0.002. Okay, and by this point we see a pattern. There's a 0.998 and the power is increasing. And we see why it's increasing by 1. That's the probability that the first k-1 trials do not show a side effect. So in general, for a positive integer k, and a lot of times somebody will just put k greater than or equal to 1 for this and understand that it's an integer, we have that the probability that x is equal to k is, well, we have to factor in the probability that the first k-1 trials do not result in a side effect, and that's 0.998 to the power of k-1, and then we have to multiply by the probability that that last treatment does result in a side effect. And we're going to discuss this type of distribution later. It's called a geometric distribution. We're going to look at what kind of a situation it applies to in the next section. But for now, I just thought I'd introduce it as an example of an infinite discrete distribution, one that has an infinite number of possible values.